What's going on, everyone? My name is Johnny Bannon, and I'm your CCNA instructor for this CCNA video series. This is going to be our part 2 of OSPF. We just left off going over the different network types, which again, I know can be confusing, especially just learning OSPF and not really being able to visualize, right, what this means or when you would be configuring these different network types. And again, that just comes with time and practice and labbing it up, right? So please just stay tuned for our labs if these network types kind of confuse you or the reasons why they'd be different. It all has to just deal with the OSPF operations, right? So for example, like with this point-to-point network, you don't need a DR and BDR because you don't have issue with LSA flooding because this is just a dedicated line. So we'd call this like a T1 dedicated line, right? Kind of old school, still around today, but it's dedicated straight from your ISP, right? To either your spoke here, this could be your hub, this could be your spoke, however that line is dedicated, right? Okay. So again, and then point to multi-point, that would be considered like an MPLS network where we have different networks or one router as the hub for all these different spokes, but logically we believe that we're just one point to point, right? So R2 thinks it's just a point-to-point network to R1. That's what we call a point to multi-point, right? Which is different than, let's say, an MBMA network, non-broadcast, but it's still multi-axis where these spokes have knowledge that they're accessing a larger web, right? Okay, so with that kind of out of the way, I just want to touch up on that again. Let's go over the OSPF rules. So when we're running like a broadcast network, right? In OSPF, we're going to have to elect the DR and BDR. And then during that, when we're building the adjacency table, right, after we establish neighborship, that's when we do the master-slave negotiation or the DR and BDR election. That's going to be based off priority. So the highest priority is actually going to take precedence and become that DR and BDR, okay? So the lowest OSPF priority is going to be a default of 1, right? That's just the default. The higher the priority, that's going to be your DR and BDR election. Now, let's say all things were left at default, right? And it's all left at 1. How do we decide the DR and BDR? That's going to be the highest configured router ID is going to be the tiebreaker. Now, okay, how do we get a router ID? Well, one, you can statically set it under the OSPF subconfiguration, or it's going to be your highest IP address on a loopback, or if you don't have loopback addresses, it's going to be your highest active interface, okay? So again, during that exchange, right, when we're starting to build our adjacency tables and build our link state databases, and we elect that DR, BDR, do the master slave, in those database description packets, we're actually going to decide the DR and BDR. And in those packets is going to be our priority number. If all things are left to default, it goes off the highest router ID. But you can change these priorities again under the interface because this is a link state routing protocol. So a lot of the times when you're configuring different parameters for OSPF, it's going to be under that actual interface, okay, configuration. Again, we're going to go over that in our labs as well. So for a router ID, it's a 32-bit address, so an IP address, right? And you typically see it in the acronym right here, RID, R-I-D. Again, it can be manually configured under the OSPF configuration, or it's going to be automatically chosen via the highest loopback IP or the highest up physical interface IP. So if we have an interface over here, let's say gig 01, and it's down, that IP address cannot be chosen as a RID, right, or a router ID. So router IDs, again, like I discussed in the other video, should be unique to every router. If you are not unique to every router in that broadcast network, we're going to run into issues, okay? Where essentially those adjacency tables may not be able to form because the way those database descriptions are sent, the router ID comes into play, and it's going to think that it's learning from 2 different devices, right, that are trying to be the same. All right, some more OSPF rules going into areas. So OSPF creates routing domains within areas, okay? So OSPF's link state databases, or the LSAs, are going to be sent within an area. And depending on the type of link and depending on what we're advertising for, that's going to be the type of LSA that we exchange, okay? So there's different LSA types that are determined from the area that LSA is routing in, okay? So OSPF does have a main area called the backbone area. And all non-backbone areas, so pretty much any area ID that isn't 0, has to connect to the backbone area, okay? So let's break that down. So again, we have our backbone area, which is always area 0, correct? Let's say this router 1, this is router 2, router 3. At some point, each router is going to have a link or LSAs, right? Or an area border router that it's connected to that's also connected to area 0. So since router 2 here has one of its interfaces into area 0, it can form neighborship with R3 in area 51. And then we can also have other routers in here, right? As long as that router eventually comes back to this area border router, which does have a configuration or a link back to the backbone area, we're able to build our different areas. Now, what happens if we get into a weird scenario where R3 is connected to R10 over here, and this is like area 76? Well, that's a no-go, because area 76 doesn't have a connection back to area 0 anywhere in any of its interfaces. R3 only has an interface in area 51, and then this would be a different area. So those LSAs that are being exchanged here will never actually connect back, and you'll never actually get full routing from like R10 to over here to R2. I've already talked about a workaround for this, and that's going to be virtual links. But again, we're not going to talk about that in the CCNA as far as this lecture portion. And then the routers that are connected to both the backbone and the non-backbone are called ABRs, or area border router. We see over here R1 is also labeled as an ASBR, and that's called an autonomous system border router. And this is when a router like R1 here is running OSPF on this link, but then it's connected to an ERGRP domain on this link, and we had to redistribute those ERGRP learned routes back into our backbone area. We call that an ASBR. You can see the different LSA types that'll be sent on these different types of router designations, right? And we're going to get into that with the LSA types here shortly. Okay, so let's go over the OSPF tables and databases real quick, because we're about to deep dive into them. So the first table we have is the adjacency database, or the neighbor table. This is going to be the first table we build, and it's just going to be a list of all the neighbor routers, all the routers we have connected to us that are also running OSPF. And then we have our topology table, and this is going to be that link state database. So this topology table has to be the same amongst all OSPF enabled routers within an area, or the area is connected back to the backbone area, to be considered fully converged. So then we can build our forwarding database, or our routing table. So this is kind of like more like technical speak, right? If you're talking OSPF, but this is just what we call it in like layman's terms every day, right? So like, hey, let's look at our topology table, right? We know if we're running OSPF, that means that's our link state database. Okay, awesome. So now let's go over OSPF formation overview. So we kind of went over this in the first video, but now we're going to get down and dirty, right? So what happens when I got two routers here and I enable OSPF on them? Well, before OSPF is enabled, before hellos start getting sent, we call that its down state. It's in a down state. So that's like us saying router OSPF in our CLI and then not doing any network commands yet, right? These interfaces are going to be in a down state. They haven't been enabled to send OSPF packets yet. And then this init state is when we start sending those hellos, okay? Now we're initializing our neighborship. And then once we come to a two-way state, that means our neighbor table has been formed. And now we're ready to start building and synchronizing our databases. So then we head into what we call on the link, our actual link goes into an X start state. And this is where we decide that master and slave relationship. So the DR and BDR election. And then once the DR master has been chosen, we're going to start exchanging. So essentially what's going to happen here is all the non-designated routers are going to send database description packets to the master. And those database description packets are going to have a summary of everything it knows about. And then that DR is going to send those databases out to every router. And then every router is going to build what we call that link state request list. And then once those lists are built, that's what we call our exchange state. So every router is now doing link state request, right, from their list. So the goal is to have that link state request list drop down to nothing, to zero, right? So in that exchange state, our routers are all talking to that DR router requesting LSA, saying, hey, we need to synchronize our link state databases, right? So that DR is going to send back link state updates, and then they're going to send back link state acknowledgements until their link state request list is empty. There's nothing there. And then once that happens, we head into what we call the loading state. So now in that loading state, that's where all of our LSA flooding is complete, right? And now once that's done and they're all synchronized, we enter into that full state, okay? So that loading state is this process of LSA flooding to that designated router, that master-slave relationship, right? And then once that link state request list is donezo, it's empty, we're in that full state, okay? All right. So let's go ahead and jump right into this. Okay, so the neighbor table. So the OSPF hello packet is essentially what makes our neighbor table, right? And all the parameters have to match. So look at the right here, we have an OSPF hello packet. And in this packet, we can kind of see, right? This is going to be for a broadcast network, right? Because we see it has information for our designated and backup designated router, and then a list of all of our neighbors. So during the neighborship building, the OSPF state moves from init all the way to two-way, or what we call druther, okay? So in that packet we're going to, again, have our router ID, area ID, authentication if we configure it. It's optional. Our hello intervals, right? Also our dead intervals. And then not right away we're going to have this information, but OSPF hello packets will have that information after we've done those elections, right, of the DR and BDR. And we're going to deep dive into this with Wireshark captures on a live network as well. Okay, so now let me draw it out for you, kind of what's happening on our network. So at first, we're going to be in a down state, right, until we enable OSPF. So these bad boys, let's say R2 here, R1, they're in a down state. Then we enable OSPF on the router, and in our network statement, we enable OSPF for gig 00 on both sides. Then we enter into what we call an init state. And this is just to build that neighbor table. So one of these routers is going to send that hello packet first, and the neighbor field of that packet is going to be empty. And the DR and BDR fields are going to be sent to 00. So they're going to send hello packets to each other. Hello. And their neighbor list is going to be empty. Once they receive those hellos, they're going to start building a neighbor data structure. And this is going to set their states, right, into officially that init state once they actually receive hellos. So now we can start building that neighbor table once these hellos have been sent. During this time, we're also going to send our priorities, right? So we're going to send our priorities as well. Okay. So once that is done, we're going to start sending database description packets. Okay. So once those priorities are sent, guys, now we're adjusting into what the X start state. Okay. And now we're jumping ahead because essentially the only two states we care about are down and init. And we also go into a two-way state once those hello packets are actually going to have a neighbor list. Once that neighbor list is populated with each other's neighbors, they get into that two-way state and then immediately start going to that X start state, sending database description packets. So you can see in the process of OSPF, the neighbor tables are formed pretty quickly. Because essentially, hellos are sent with an empty neighbor list and empty DR and BDR fields. And then those are quickly built, right? The neighbor list is built, and then the DR, BDR fields will be built after we go through our X start state, which we're going to get into when we build the adjacency table. And again, it's not always a perfect flow in OSPF as you're going to see in our labs. But again, this is just from documentation from the RFC, right? What happens. So now we built our neighbor table and we're entering into our X start state. So this is when we form our actual topology, right? So to start building, we first send database description packets. These are going to update our link state request list. And then from our link state request list, we start sending LSA request messages, LSA update messages, and then acknowledgments as well. And this is what's going to allow us to fully converge our link state databases. This is the LSA flooding. So during this process, we will go through our X start, exchange, and our loading states, leading us to a full state. So let's just dive into what a database description packet looks like. So you can't see here because it's cut off, but essentially there was just like two other hello packets, right? And after this third hello packet, we immediately start sending our database descriptions because we have to build that DR-BDR relationship. We got to send a summary of our link states, right? So pretty cool as you can see here. We can see that MTU, which has to match, right? We can see this is saying, hey, I'm the master with this bit right here. And these bits all mean something and go into the sequencing of our X start, exchange, and our loading state. Well, you can see the first database description here. It's just going to set the DR-BDR relationship. And then these bottom two are going to have our link state summaries in there. And from that, that's when we actually start seeing our link state requests and updates, right? So now let's go into a link state request and what that packet looks like. So it's literally just, this is it. This is an entire link state request. You can see in here the OSPF header. We still have our area ID. This is coming from 1.1.1.1. That's the router ID, right? We can see that this is a type 3 LSA. Now this, well, let me back up. This OSPF header is a type 3, which means it's a link state request, not to be confused with the LSA types, okay? So in this OSPF header, we have this field here, and if it's marked 3, we know that it's encapsulated for a link state request, right? That header is encapsulating this link state request. So in this link state request, we're asking for type 1 LSAs, and we're saying, hey, this is us, right? We need to, this is me. We need to know about all the LSAs in your database. So then once that DR receives this link state request, it's going to send back a link state update. You can see that OSPF header, it's a type 4, which again, it's an OSPF header type 4, which means this is going to be an LSA update. You can see the area ID here. Right, of course, just if we had authentication, still making sure that we're advertising or updating the right neighbors. This is going to be a type 1 LSA, which means an LSA within the backbone area. And look, it is advertising all the networks it knows about. Pretty cool, right? So now this is how the router receiving this, the one that sent the request, is going to place these routes into its link state database. And then it's going to send an acknowledgement back saying, cool, I have learned about these routes. And again, this is going to be a type 1 LSA, but you see the OSPF header here is a type 5, meaning it's going to be a link state acknowledgement. So this acknowledgement is just saying, cool, I have added these into my link state database. Pretty much just saying, we got that update. Don't send it again. Okay, and now let's go over the LSA types. So not to be confused with this right here, this is the message type, not the actual LSA itself, that link state advertisement, right? So type 1s and type 2s, those are going to be within an area. Those get sent to advertise within an area. Type 3 or 4, area border routers are going to create those to send into the backbone area. So the backbone area learns about the non-backbone area routes. And this is just going to be a summary, meaning if this area 51 has 10.10.0.0 through 10.10. Let's say 31.255 networks within this area, right? So it could be multiple routers. This LSA type 3 right here is just going to say, hey, if you want to get to this network block, come this way. We're not going to send you 30 individual routes for every single network within this range, right? It's a summary, essentially. And then we have type 5s here, and these are going to be external LSAs, meaning we're learning about this network, this LSA, from a non-OSPF routing protocol. And that's as far deep as I'm going to get the LSA types. We can see here we have multicast OSPF LSAs, type 7s, which are not so stubby areas. External attributes LSA for more fine tuning you can do with BGP. And then we have these type 9, 10, and 11s, which, to be honest, off the top of my head, I don't know what they're used for. Probably just so you can make your own LSA type, right? But again, really the only ones on the CCNA exam you need to know about are type 1 and 2. Okay, so now let's go over the adjacency table. So, or this can be better described as the link state, right? Database, link state database, or topology table. All right, so we start out in the X start state. And in this X start state, we're going to send database description packets that are going to decide the DR and BDR. So let's just say that R1 is designated as the DR, right? It had a higher priority, let's say priority of 100. Once we decide the master and slave negotiation, we're going to head into the exchange state. In that exchange state, R2 here, so now we've entered that exchange state after we determined who the DR is going to be and the BDR, right? If we have more than just 2 routers here, which in this case, R2 would just be the BDR, right? In this small network. Now in this exchange state, we're going to send database descriptions. And the purpose of these is to figure out what we know about, right? So we're going to send summary LSAs. Summary LSAs. Now they're going to look and reference this database description packet to their link state database, and they're going to build what we call the link state request list. Link state request list. The first router to do these requests is going to be this BDR, because essentially every single router in this network should have been sending those database descriptions to the DR, meaning this database description with the summary LSA from R2 should only have gone to here. So the DR should know about every single router summaries, right? and say, okay, I got my master list here. And then he's going to send out a database description saying, here's what you should know about. And now R2 and every other non-designated router, let's say this is R3, is going to be asking, hey, we need updates because we have a long link state request list. And we need to know about these LSAs. So they're going to go, not necessarily one by one, right? But the DR is going to send all them link state updates. And they're going to send back link state acknowledgement. So in that exchange state, now we're sending LSA updates to our non-designated routers. And our non-designated routers are sending link state request and link state acknowledgements. And we're going to do that until our link state request list is empty. You see here, there's nothing there. And then once it's empty, and once the DR sees that all the link state request lists are empty, we're going to head into a full state. Or excuse me, a full state. And once we're in that full state, that means now our routes can be placed into the global routing table. Okay? During this link state flooding, this LSA flooding, I'll call this, that's when we're sending updates, requests, and acknowledgements. This is going to be the loading state. I missed a step there. Loading state. Right, and then once that link state request list is empty on all routers, then they enter the full state. Okay, and that's kind of just a summarized version of how we build that topology table, that link state database. All right, now building the forwarding database. So building our actual routing table. Now that we've gone through the neighbor table and the link state database, our topology table, now we need to build our global routing table so routers can actually pick how to send packets. So now we're going to execute the OSPF algorithm, or the shortest path first algorithm, which again is going to be that reference bandwidth divided by actual bandwidth. And lowest cost is going to be the best path that goes into the global routing table, right? So I see a mistake here. I'm just going to get this off. Okay. Awesome. So building that forwarding database, again, if we were to draw it out, really it's pretty simple. We have our link state databases here. Link state databases. We're just going to run that SPF algorithm on our link state databases, and then that's going to build our routing table. Awesome. So now let's go over that OSPF metric and see how we actually build the cost, right? How we get that lowest metric. So our reference bandwidth is always going to be essentially 100 megs. Okay. So that means we're dividing the actual bandwidth always by 100 megs. This is what it would be in actual bits per second. So what do you see here as the inherent flaw, right? So we understand how we get our cost, the reference bandwidth minus interface bandwidth. Well, essentially with this original algorithm, fast Ethernet, gigabit Ethernet, and 10 gig Ethernet, all the same cost. So that means if we have a network like this, where this is 10 gigs and this is 100 megs, we're going to think these are equal, and we're actually going to load balance across these, which, may not be a bad idea, but really this should be the primary. This has the better cost. We should be using that 10 gig link, right? I mean, load balancing, it would be a horrible idea here, right? 10 gigs is significantly more. So we can actually change this reference bandwidth to, let's say, 1,000 or 10,000. And most of the time, if we change it to 1,000, that's going to work for a lot of our small to medium businesses, because the most we're going to get out of a link maybe will just be that gig. And it just depends on your environments, right? but know that we can change this reference bandwidth to reflect the higher speeds in our modern networks. And we're going to show you that in the labs as well. All right, so we're going to quickly go over OSPF configuration here because, again, during our labs, when we're really going to hone in on that, right? So one, to enable OSPF, real simple. Router, OSPF, and then a locally significant router process ID, right? So this number can be different on all your routers, and it has no plan whether or not OSPF is going to work, unlike something like ERGRP. And then this also is optional. Forgot to kind of put that in there, but under the OSPF process, you can set the router ID here. Again, the router ID is a 32-bit value, right? So we can express this as an IP address. And then to actually enable our OSPF interfaces, right, to get these links to become part of OSPF, we do something called the network command, which is going to be the network address that we want to enable, and then a wildcard mask, which is essentially the inverse of a subnet mask. And I will show you that in our labs, how we get the wildcard mask. Essentially, a quick shortcut is you take all 255s and then minus your subnet mask. Again, this is going to be in dotted decimal format. And you get your wildcard mask from this subtraction, okay? Essentially, this is being very specific on the host count, right? That's what a wildcard is used for. And then very important in OSPF, you have to set the area you're going to be routing for. So again, for the CCNA exam, just doing single area OSPF configuration, this is going to be what you need to know. Area 0, right? Everything's going to be area 0 for the CCNA exam. And then you see the full configurations here. Okay, so verify OSPF neighbors. Quick command, show IP OSPF neighbor. It's going to show you the neighbor's router ID, the state you're in, right? You can see here that there is no DR and BDR, so maybe these are point-to-point links, right? Something you need to kind of recognize as well. And then you can do show IP protocols. This is going to show you all the routing protocols enabled on your router, and then the networks that you're advertising here. And then show IP OSPF interface brief. Another awesome command. It's going to show you the network type here, the state, right? So point to point, and then DR, BDR. So that's going to be a broadcast network, right? It's going to show you the cost of that link, the area it's in, and then the router process ID. So this is part of OSPF process ID 10. And then, of course, the IP address information. Awesome. So again, quick on the last section here, but please feel free to go back and watch the video over again. We went over a lot, especially when it came to forming OSPF, right? OSPF formation. If anything, you really need to remember is just these states right here and just kind of quick synopsis, right? Know that the synchronized the databases is when we enter into these states. And this is when we're sharing LSAs, right? Getting down to the nitty gritty for CCNA, not too important, right? And then understand that this neighborship is going to be, or establishing neighborship, you enter the init state, and this is all just your hello packets, right? Awesome. So in a point-to-point link, right? This process still happens, but we don't have a DR BDR. So really, you just kind of enter a full state. And again, we're going to show you that in the labs as well. All right, so I want to thank you for viewing and stay tuned because we have a lot of labs to go over. So we're going to do one simple lab of OSPF, get it up and running, do a Wireshark capture, be done deal, right? And then we're going to do what I call an advanced OSPF lab, where we're going to hit all the CCNA exam objectives in the lab. So we're going to set priorities. We're going to show you a point-to-point link. We're going to change the hello and hold timers. Also going to show you, bonus videos are going to have multi-area and all the other types of OSPF configuration we can do. Those are just bonuses. Essentially, what I want you to become familiar with is the difference between a point-to-point and broadcast network. changing the hello and hold timers and how it affects it, right? How you don't create neighborship, and then setting the OSPF priority ID before OSPF forms, neighborship forms, and after neighborship forms, will that new priority take precedence and become the DR? So we'll figure all that out, right? So please stay tuned and thank you for viewing.